We're going to look at the shape and the real roots of polynomial equations using Microsoft Excel. In this yellow box, we specify the powers for each x term and the coefficient, and that will define f of x. In this section here, we will specify a range of x values over which we would like to see a plot. So let's start with this equation here. F of x equals 6x cubed plus 5x squared plus 7x minus 20 equals 0. It's a cubic equation. So we already have a 3 up in the power array. So under the 3 we will enter 6. Under squares, we have a coefficient of 5. For 1, the coefficient is 7, one single power. For the 0th power, the coefficient is minus 20. Now we need to specify a range of x values over which we would like to see a plot, over which we would like to examine the shape of this curve. Let's start with minus 5 to plus 5, see what we have. Okay, that's a reasonably good range to look for. So there we see a typical cubic curve. In polynomials, the highest power controls the shape of the curve for large values of x, large absolute values of x. And for odd powers, it starts in negative infinity and goes off into positive infinity. And if the coefficient of the cube is negative, of the high power is negative, it'll flip around the other way. Okay, so the interesting part that what we want to look at is the part near 0. The red line defines y equals 0. So if any place where the blue line crosses the red line is a place where there is a real root, that means a value of x at which f of x equals 0. A value of x at which this equation is satisfied. So let's look for the roots. Zoom in to the minus 2 to plus 2 area to see what we see down there. And there it looks like there is a root right around 1, right around x equals 1. This f of x should be 0 when we set x to 1. Let's see if that works. Down here we come to the root area, root section of this spreadsheet model, and we're going to test an x equal 1 to see if f of x equals 0. It is not. It's somewhere near 1, but it isn't 1. So we'll go to Excel's data section, go to the data tools part of the menu, to what if analysis, and select goal seek. Goal seek will try to set a value of a cell to a specified number by changing the value of another cell. In this case, we want to set the value of f of x to 0 by changing the value of x. And click OK, and it has found a root. The root is 1.06, and f of x is 0 at 1.06. And that's how you work with polynomials in Excel. How does it work? Well, up here we have the array of powers and coefficients set up. So for any value of x, we should be able to compute f of x. Here we specify a range. And down there, well below our root section, we compute 40 values of x arbitrarily. I picked number 40. 40 values of x between the minimum and maximum value specified in the range up here, within the range. And then for each value of x, compute the value of each term of the polynomial. Some of them will be 0 because we don't always have every power in the equation. And then when you add up all of these terms, you get f of x. And once you have x and f of x, you can use Excel's scatter plot tool to make this graph. And when you find a possible root, then you come to this section here, guess the root, compute f of x using the same procedure that we used down here, and then use the goal seek tool of Excel to find the value of x at which f of x is 0, and for each candidate root. So let's try this with another example, a fourth power. Well, before we do that, let's examine what happens if we add for a power that's not here. We could add, for instance, let's say a 1 coefficient for a 9th power. And if I make that 1 minus 1, now the 9th power controls this curve. The highest power of the polynomial always controls the curve outside, at large values of x outside of the middle. So now we have a totally different curve, but we can find the roots once again by guessing here, probably minus 1.5, and zoom in on this section. Look at 0 to 2. And it looks like there's a root between 1 and 1.5. There are two roots between 1 and 1.5. One at closer to 1 and one closer to 1.5. So let's find those roots by guessing 1 and 1.5 down here in the root section. 1 and 1.5. These aren't roots because the result is 0. So let's use goal seek again. Set f of x to 0 by changing x. The root is 1.13, and the one that's right over here, that's 1.13. So now let's guess 1.5 to get the other root. Goal seek. Set f of x to 0 by changing cell, this guy here. And there's the other root. The other root is 1.31. And if we go back now to minus 1, minus 2, okay. At minus 1.5, it looked like there was a root. So we could check that as well. Minus 1.5. It's not 0, so minus 1.5 is not the root. We're going to have to use goal seek. Set f of x to 0 by changing x. The root is minus 1.51. So these are the three roots of this equation. Now let's look at a different equation. Here we have a fourth order equation where the fourth order coefficient is 3, third order -5, second order 2, first order -1, 0th order 10. And we give it a range, start with -5 to +5, I always do. And there you have a typical fourth order polynomial curve. It looks like a pot without a pan without a panhandle. It faces up if the fourth order coefficient is positive and faces down if it's negative. But the interesting part is right around here. It's between -2 and 3, +3. Let's look at that part. Zoom in, -2 to 3. And there it is. It never touches the red line. There are no real roots to this equation. Let's try another fourth order equation. Here the fourth order coefficient is 1. The third -5. There is no second order term. The first order term is 20 and the 0th order is -16. Let's give it a range. And -5 to 5 we have an interesting section here between -2 and +4. So let's look at that. Zoom in, -2 to 4, and it looks like we have 1, 2, 3, 4 roots. One at -2, at 1, 2, and 4. -2, +1, +2, and +4. Let's check those. -2, 1, 2, 4. They're all roots. We don't have to use goal-seek because f of x is 0 at each of those values. We have solved the equation. And we can see it visually that at each of these points f of x equals 0 because the red line represents y equals 0. Here's another example. This is a fifth order equation. The 5 power coefficient is 1. Then we have an 8, 20, 10, -21, and the constant term is -18. Let's start with a range of -5 to 5. That's not a good range. Let's try -6 to 4. -6 to 4. There. Now we see the whole typical odd power curve with some interesting stuff between -5 and 2. So let's just zoom in, -5 to 2. There. Looks like we have a root at halfway between 0 and 2 at 1. Let's see if that works. 1. Yes, that is a root. Okay, so go back up. Zoom into this part here. -4 to 0. -4 to 0. And there we see there is a root at -3 and one at -2 and one at -1. -3, -2, and -1. Let's check those. -3, -2, -1. And by golly, they're all roots. We don't need to use goal-seek in this problem at all. Of course, if you look at this equation with your algebra skills, you'd be able to factor it. And what would those factors be? X minus 1 times x plus 3 plus x plus 2 times x plus 1. That's another way to factor. You can use Excel to factor polynomials. Let's look at quadratic equations. You can use this tool to solve quadratic equations as well, because a quadratic equation is just a polynomial with where the highest power is 2. put in your coefficients. The second order coefficient is -2, first order -5, 0th 4. Put in a range. I always start with -5 to 5 and then change it. I don't need to change it. I'm looking at a very interesting part of the parabola. Here's your parabola facing up. When the quadratic term, the second order term, is negative, the quadratic will look down and peak up. When it is positive, it'll face upwards. So let's turn it back to what our equation is and look for roots. There's one at -3, right around -3, and there's one somewhere near +1. Let's try those, +1 and -3. 1 and -3. They are not roots. We're going to have to use goal seek to find them. Set f of x to 0 by changing x. Okay, 0.64 is a root. Now let's see what the root is that's near 3. Goal seek. Set f of x to 0 by changing x. It has found another root. So 0.64 and -3.14 are the two roots of this equation, as you can visually see over here, where the f of x crosses the y equals 0 line is where f of x equals 0, and the value of x at which f of x equals 0 satisfies this equation. Another quadratic example. This one you will recognize from your algebra skills. That is x squared minus 6x plus 9 equals 0 would be x minus 3 squared. So there should be only one root at 3. So let's check it again. Put in your coefficients. 1, minus 6, 9. You have to write the equation in standard form by bringing everything to the left hand side and having only 0 on the right hand side of the equation. And that way, in that form, it would be x squared minus 6x plus 9 equals 0. Let's pick a range of -5 to +5. Okay, let's try 0 to 5. There. Now we see that there is a root at 3. Check. Punch in 3 over here. Yes, it is a root. Yet another quadratic example with coefficients 2, -5, and 1, and range of -5 to 5. Okay, there are two roots apparently, one near 0 and one near 2. So let's zoom in to -2 to +3 and take a look. -2 to 3, and there is one near 0 and one near 2. We go to the root section, put in 0 here and 2 there. They are not roots, of course, it's near there. So let's start with this guy here and goal seek. Set f of x to 0 by changing this x over here, and 0.22 is a root. Let's check this number here. Goal seek. I set f of x to 0 by changing x. And 2.28 is a root. So there are two roots to this quadratic equation, and we have found them using Excel. So to solve any polynomial or quadratic equation, all you need is Excel.